Bridge. How are you doing? It is week 5. It's the second assignment. We're going to be finishing this week off by wrapping up solving exponential equations and using our logarithms here. I'm going to give you a couple more problems. They're going to be a little bit trickier, but not too bad, all right? So hang in there, and I'm planning for this video to be very short, all right? So you'll get some examples, and then you'll have some time to work on that assignment. Anyway, I got a bridge of the day. Super cool, super cool. It is in South Korea. It's the Incheon Bridge. Probably not saying that correctly, but that's okay. In South Korea, very pretty. Okay, let's take a look at our first example. In 2020, you decide to start saving. You decide to start saving money in a savings account with a deposit of $1,000. All right, so I'm depositing $1,000. Again, if we're thinking about our exponentials being in the form of a equals p times 1 plus or minus r to the power of t, that initial deposit of $1,000 is going to be that p value. The principal is what we call it. It earns 1% a year in interest, so that sounds like our rate. All right, that's my R value. And 1% as a decimal is going to be 0.01. I just moved that decimal place over twice here. So I have a decimal rate of 0.01. And then there's two questions here. All right, question A says, how much money will the account have in 2030? All right, notice how I don't tell you how much time has passed in years. That's something that you've got to figure out by yourself, all right? And this one's pretty simple. How much will the account have in 2030? Well, I started this in 2020, so 2030 minus 2020 gets you 10 years. So I know my t value would have to be 10. Now I'm going to set up my exponential equation here and say, we're trying to find out how much money the account will have after a certain amount of years, so I don't know my a value. So I'm just going to say a equals 1,000 times 1, what do I use, plus or minus r? Well, I'm gaining interest. It's going to be earning interest, so this sounds like exponential growth. 1 plus my rate of 0.01 to the power of, again, we decided on 10 years. And now this is like throwing it back to really early in this unit, just simplifying a simple exponential. So I'm going to take this step by step and say that a equals 1,000 times, I'm going to add those together in my parentheses, so it's 1.01 to the power of 10. And then according to my PEMDAS rules, right, I got to make sure that I do my exponent first before I multiply these together. So it's going to be 1,000 times whatever 1.01 to the 10th power is, and that gets you a decimal of 1.104622. It just keeps going on, so I'll just cut it off there. And then I can take that number, I can take that answer and multiply it by the 1,000, which essentially is just moving the decimal place over 3 spots since I'm multiplying by like a power of 10, right? So my answer here is going to be, after 10 years, you have earned $104.62 in interest, all right? That was part A. Part B. How long does it take for you oh my gosh, can I read today? How long does it take for the amount to double your money? All right. So doubling your money, again, now our A value has to be twice, is 2 times our principal amount, right? So we initially deposited 1,000, so I want to know how long is it going to take for my account to reach $2,000 at this rate. Well, and seeing after 10 years I've only earned $104 in interest, my guess is probably going to be quite a long time. Let's solve for that time though. I'm going to keep the same deposit of $1,000 multiplied by 1.01. I got to keep that interest rate, but now I'm solving for t, so I'm going to keep that unknown variable up there, t. So I'm going to start to solve by dividing by 1,000 on both sides. I want to get this to a very simple and basic exponential. 2,000 over 1,000, that just simplifies down to 2, equals, those cancel, 1.01 to the power of t. Now this is a simple exponential that I can write in logarithm form. So I'm going to do that. I have a log. I have a base of 1.01 of 2 has to be equal to my exponent. And then I can use the change of base formula to figure out what that side is. So I'm going to say that t is equal to, using my change of base formula, I'm going to pick a new base of 10 and say log base 10 of 2 divided by log base 10 of my original base, which was 1.01, and then you can just plug that into your calculator and simplify. I got a t value of a very big number, 69. Well, it's not very big, but you know, would you like to wait 69.6 years to get your account to double its money? You may want to go find a new savings account. All right. So there we go. Again, this was a two-part question. The first part was, well, just set up the exponential equation and evaluate it. The second part, since we had the exponential equation set up, we were able to solve using logarithms a little bit more complicatedly. Is that a word? I don't know. All right, let's move on to the next one. I got a fun one. I actually thought about this and I was like, oh, it's going to be cool. All right, I'm going to hit cut. Bye. Alrighty, so this is the second example that I have. I think this was pretty fun. We're going to just look at some shapes here. This is an equilateral triangle, or I think it looks pretty darn close when I drew it. And I'm saying you can divide this triangle into smaller equilateral triangles. If you were to divide this into smaller equilateral triangles, well, I have to keep all the sides the same. I'm saying, you know, you could draw these lines in here that I'm doing right now. And that gets you some smaller triangles, right? Okay, my drawing's not perfect, but you get 4 smaller equilateral triangles, all right? So that's essentially what I'm asking you to do. And what we're going to do here is it's going to say how many triangles will you have after 6 divisions. So if this is like starting with 0, after 1 division, I have 1, 2, 3, 4, right? So I'm going to put this into a table of values, which is going to help us make an equation out of it. So let's say that this is the number of times we've divided. I'm just going to say number of divisions we've made, right, after the first set, after the second set. And this is the number of small triangles that we have, all right? So after 0 divisions, right, this is our starting point. I just have 1 large triangle, all right? And I'm starting at 0 so that we can have an initial value later on that's going to help us. After 1 division, so just like I said, you could take it like this and divide it like that. After 1 division, now I have 4 smaller triangles. Now if I can divide all of these smaller triangles into more smaller triangles by doing the same division. So I'm going to cut these down even more and say, okay, here is our second round of dividing our triangles into smaller triangles. And if you count all of those triangles up, there's 1, 3 here, 1, 2, 3, there's 5 there, right? If you count all of those up, you're going to get a total of 16. So after 2 rounds of cutting up our triangles, you have 16 triangles. Okay, let's cut all these up. Let's do a third round of division on all of these guys. So I'm going to say, I'll put this in a different color so we see and keep track of. Here's my third round of division. I probably should have been saying that as I did this, but I do want to show you all of it so you see exactly what we're talking about. All right, and I'm not going to go through and count all these, but if you count this one and this one, 3, 4, 5, 6, 7, 8, all those little triangles, you will count that you actually have 64 of these really small triangles in here, all right? And you could just keep doing this forever and ever and ever, right? I mean, you may actually run out of time in the universe, but you could keep going and just making these triangles smaller. So I'm asking, after 6 rounds of division, after cutting these things like 6 different times, right? How many small triangles are you going to have? Well, instead of actually drawing this out, let's see if we can just come up with an equation, okay? So, again, we know all of our exponentials can be written in the form a times b to the power of x. And essentially that's what we did up here, right? We had an A value of 1,000. Our B value was 1.01. So down here again, my A value is my initial, my starting value. I see that I'm starting with just one big triangle. So I know y equals 1 times, well, what's my B value? What am I multiplying by every time? And if you see, that's just multiplying by 4. Well, that's just multiplying by another 4. Again, we're just multiplying by another 4, right? So my 4 has to be my growth factor here. And if you have just one triangle, cutting it the way we did, you get 1, 2, 3, 4. So it takes 1, makes 4 triangles. All right, so that's our growth factor. Anyway, I'm multiplying by 1, so I don't really need to write that 1 there. It's just kind of redundant. So I could just say that I have this formula of y equals 4 to the power of x. Pretty cool. So here would be like our x values, and these would give you your y values, all right? And I'm asking, how many triangles would you have after 6 divisions? So when we have 6 rounds of division, you know, after x equals 6, let's just plug that in here. So I'm going to say that part A, y equals 4 to the power of 6, and that's just a quick one. Well, 4 to the power of 6, I plugged that into my calculator, and I got 4,096, okay? So if I continue doing this a couple more times after 6 rounds of cutting all these triangles up, I would have 4,906. I'm glad we didn't actually do that, and we could actually find some math instead of physically counting 4,000 triangles. Part B now. It asks, how many divisions will it take before you have 10,000 smaller triangles? Okay, so now I'm asking, if I have 10,000 smaller triangles, how many rounds of cutting did I have to do here? So now I'm solving for x. Now I know what my y value is, so I'm going to put 10,000 equals 4 to some power of x here, right? That's what we're solving for to the power of x. And then we can just use our logs, all right? So this is a simple exponential equation, so I can just write this in logarithm form and say log base 4 of 10,000 equals x. Use my change of base formula on that and say, let's pick a new base of 10. So log base 10 of 10,000 over log base 10 of 4 equals x. And you plug that into your calculator. I got an x value of 6.63. So I would have to start making these divisions on my triangles 6 times, 6 rounds of dividing all these, right? And then I would get 10,000. And that kind of makes sense here, right? When we did 6, we had 4,000 triangles. So if I, technically if I round this up to 7, if I multiply 4,096 times one more 4, you get 16,384. And 16,000 is indeed greater than 10,000. Oops. Then why is my pen not working? Yeah, 16,000 is greater than 10,000, so that checks out, right? I'd have to do a little bit more than 6 in order to reach 10,000 smaller triangles. Okay, that was kind of fun. I like that problem. I think I'm gonna keep that one around. Have a great day, you guys. Keep doing what you're doing. And for those of you who have stuck around this far, I'm giving you another little cute video of an animal. All right. This is Henry from my other aunt. She loves this little dog. New little dog, very cute. Runs around. Actually, I haven't seen the video yet, so he's small. It's adorable. Okay, here's Henry, the cute little dog. Go team!